In this lecture, we will be learning about derivatives of vector-valued functions. So recall, a parametric curve C in R3, three-dimensional space, is a triplet of functions x equals f of t, y equals g of t, z equals h of t, that give x, y, and z as continuous functions of parameter t in some domain I. And we call the equations x equals f of t, y equals g of t, z equals h of t parametric equations. And we can define the position vector for this curve C as r of t equals, and we have these f, g, and t as the components of the vector, which is a vector-valued function. And recall the idea is that if you have a particle moving in space, tracing out this parametric curve C, then at time t, r of t, if we started at the origin, points to the particle. And as this particle moves, this vector, when kept beginning at the origin, will track the point. And recall the formal definition of such a vector-valued function is that it takes in a value for the parameter t and outputs a vector in R3. Now, as students of calculus, we want to differentiate things. And we define the derivative of a vector value function at the point t if the components f, g, and h each have their own derivatives at time t. And those are just ordinary single variable function derivatives. The derivative of this vector-valued function is itself a vector-valued function, written this way. We write it as r prime of t. We'll also write it as dr dt. And here is our definition of derivative, which will look familiar. We take the limit as delta t goes to 0 of r of t plus delta t minus r of t over delta t, which is the difference quotient we've come to get used to when we work with derivatives. We remember from single variable calculus, the derivative of a function f was written this way. And so we see this modified difference quotient for the vector-valued function. And we often write it this way. Or equivalently, you may see it often written x prime of t, y prime of t, z prime of t. In understanding derivatives already from single variable calculus, we're kind of set up for this. This is a fairly natural version of the concept of derivative in this vector-valued function setting. We also have another interpretation of r prime of t, and we call it the velocity vector. And so we'll often call the derivative of that r of t, when we think of r of t as the position vector, v of t, the velocity vector, as r prime of t, which will be tangent to the curve C. So when we have that same type of picture, and we have a curve in space, and we think of the position vector telling us where the particle is. So if we're at time t, and this is our position vector, then our velocity vector is tangent to the curve. It points in the direction which the particle is moving, the instantaneous direction, and its length, its magnitude, is the speed at which the particle is traveling at that time t. So the magnitude of that velocity vector gives us the speed. And if you want the direction of motion, which we will later call the unit tangent vector, we take that vector v and we normalize it by its length to get a unit vector. Let's look at our classical helix example depicted here. So r of t is cosine of t, sine of t, t. And let's compute the velocity vector. So v of t, or r prime of t, and we differentiate each component. So the derivative of cosine of t is minus sine of t. The derivative of sine of t is cosine of t. And the derivative of t is 1. And so let's take a look at a couple examples of different times for what this vector will look like. So for instance, let's think about the time t equals 0. So the velocity vector at time 0 will be minus sine of 0, cosine of 0, 1, or 0, 1, 1. Now if we draw that vector beginning at the origin, we would go out 0 along the x-axis, 1 along the y-axis, and 1 along the z-axis. And this would be our vector here. And if we draw that here, the scale is a bit different, but the idea is right, that this is tangent to the curve at this time value of 0. Now recall, at time 1, we should label this. This is v of 0. At time t equals pi over 2, we have v of pi over 2 is minus sine of pi over 2, cosine of pi over 2, 1, and we know sine of pi over 2 is 1, so we have minus 1, cosine of pi over 2 is 0, and we have a 1. And so in this case, our vector goes minus 1 along the x-axis, 0 along the y-axis, and 1 along the z-axis. And so we're pointing this way. And so what happens here is this is our v of pi over 2. And so we can see that these velocity vectors you see depicted here are showing us instantaneously what the direction of travel is for this particle that is moving around this helix. And again, the length of these give you the speed. And you can actually check what the speed is in this case. So the speed is the magnitude of the velocity vector. And notice what happens when we take the magnitude in this case. We have a minus sine of t squared plus cosine t squared plus 1 squared, which is the square root of sine squared t plus cosine squared t plus 1. And we know sine squared t plus cosine squared t is 1. And so we have root 2 being the speed for any t. So this is moving at a constant speed while the particle traces out this helix. In the same setting, given our position vector, if our velocity vector is also differentiable, then its derivative is the acceleration vector. And so to do so, we take our time derivative of the velocity vector, or second derivative of the position vector, or f double prime of t, g double prime of t, h double prime of t. If we look at our previous example, we can take the derivative of this velocity vector. Derivative with respect to t of negative sine of t is minus cosine of t. The derivative with respect to t of cosine of t is minus sine of t. And the derivative with respect to t of 1 is 0. And so recall that we had time 0. We were at this point here. And we had velocity vector like this. And then we also had at time 1, or rather time pi over 2, we had a velocity vector like this. If we check our acceleration vector here at time 0, we get minus cosine of 0 minus sine of 0, 0, or minus 1, 0, 0, which is of course the vector minus I. And we see that would be pointing in this direction here. So there is our A of 0. If we check at time pi over 2, we see that A of pi over 2 is minus cosine of pi over 2 minus sine of pi over 2, 0, or 0 minus 1, 0, which is the vector minus j, which points, it's a unit vector pointing in the negative y direction. And if we check one more, say A of pi, we have minus cosine of pi minus sine of pi and 0, or 1, 0, 0, which is the unit vector I, and we would see that over here, this is our A of pi. And so in this example, it actually is the case that we have a right angle between the velocity vector and the acceleration vector. This happens when you have the velocity vector having a constant length, which we'll see this explored in a theorem in a lecture a little bit later on. But you see this is what we call the normal part of the acceleration, because you have this path that's curving in this inward fashion. If we look at another example, back to our example that was this kind of slithery path, if we calculate the acceleration vector, we see that we get A of t is 0 minus cosine of t, 0. And if we checked, say, at time 0, we would have the acceleration vector being 0 minus 1, 0, which would be this vector pointing this way. All right, it would be minus j. And if we wanted to pick, say, the acceleration vector up at this first peak, then we would say at time pi over 2, we have the acceleration vector being 0 minus cosine pi over 2, 0, or 0, 0, 0. And so we would actually get the 0 vector here. And so momentarily, you have no acceleration, and that's basically because you're changing, the path is changing direction. So another example, just how we see it is fairly natural to calculate velocity vector, acceleration vector. If you wanted to go one more, it would be called the jerk vector. Using our knowledge of differential calculus just kind of expanded into this vector calculus setting.